Hey class, today we're going to work on something really, what I think is cool and applicable, is we're going to take everything from this unit and we're going to now place it in the real world. And we're going to talk about how parts of a polynomial function can represent real life events, which is really what we did in the quadratic unit. Remember when you guys picked your own picture and then you modeled a quadratic off of it. But of course, like a lot of you guys picked the St. Louis Arch. The St. Louis Arch didn't go underground just like a parabola showed that went on and on forever. It only modeled part of it. So we're going to talk about the practical applications of the polynomials in real life events, but also like only the sections that represent it, not the whole picture. So right here I have a polynomial, and you guys have this at home too, so I know it's a little blurry. I tried zooming in as much as I can, and it ends up when I printed it, my printer wasn't compatible with the picture, so that's why. So if you want to note, this equation was made by y equals negative 0.0002 times x plus 30, x minus 15, x minus 45, and x minus 50. So this is factored form, obviously. So talking about this polynomial in the sense of how we've been talking about is if these are its factors, that means it hits the x-intercept at negative 30. Yep. Positive 15. Yep. Negative 45. So x minus 4, that's positive 45. Yes. And positive 50. Yes. Note that there is this negative in the decimal. All this does is scale this shape big or small. So remember, this is factored form. So like the other day, we took factored form and multiplied all these together by the box method and got standard form. So we have some really big x's, right? X times x times x times x. This is an x to the fourth equation. But on the other end, that means I would have done, to get my last value, my constant, 30 times negative 15 times negative 45 times negative 50, which is a huge number of the constant. So that's why we have this a value out front that scales this all down after the fact. You need to think about this for the upcoming project that we are going to do. But okay, this made a polynomial. We're very familiar with the polynomial. It's x to the fourth, so that's a quartic polynomial. Look at the end behavior. It goes down both ways. But that's looking at it in a mathematical sense. Let's go away from that and go to real life and look at it as a practical sense, real life practical. So I'm going to tell you now that part of this actually represents a roller coaster story where height, the y, is represented in feet, and the x-axis is time in seconds. So now we want to look at this as this is modeling a roller coaster. Now there's some things to immediately think about. We know this is a polynomial, so they have arrows on both ends, which means it goes on forever. But roller coasters don't go on forever. So there's some restrictions on what's going on for real life. So in life and roller coaster building, what are some restrictions on time? Take a moment, think to yourself, what are restrictions on time? All right, hopefully you had a good think with yourself. And some restrictions on time. Well, time can't be negative. You can't say I ran a negative 30-second mile. It makes zero sense. So time can't be negative. And I mean, time can't go on. Well, time can go on forever. But in roller coaster building, it can't be an infinite amount of time. Or else you would get on the roller coaster, age on the roller coaster, and just keep going around and around forever and never get off and never live your life. Think about roller coaster building in the sense of height. What are restrictions in life on height? Well, think to yourself, and then we'll come back. All right, hopefully you thought to yourself about height and roller coasters. And I know you guys aren't construction workers and you don't know everything, but there's codes to follow. For instance, how high something could be. There's no roller coaster that can probably withstand being the same height as the Eiffel Tower. Yeah, probably not. That's really tall. So there's a certain amount of height. I'm pretty sure King the Ka is a little over, I think 400 or 500 feet. Most likely it's not getting any taller than that. Also, you can't go down forever. Can't go underground forever. So there's got to be some kind of restriction on how low you can go underground. Well, there are tunnels and roller coasters. You can go underground in roller coasters. So we don't want to say, no, there's no negative heights, because there are negative heights. Negative heights take us underground. But we have to be very thoughtful in the process that you can't have a tunnel that probably goes more than 200 feet under the ground. I mean, again, we're not roller coaster builders, and we don't know the code for that. But we do know that it can't be an infinite amount, or else we're going to hit the core of the earth, and that gets really hot, and then our roller coaster is going to melt. And then the people who go in the roller coaster are probably going to light on fire, which wouldn't be good either. So in this specific case, this graph, this is the whole polynomial. We now know that this whole polynomial can't represent a real life roller coaster, because here is my x-axis. I know that anything over here is negative time. And I know we can't have negative time, so I know that this whole part of the roller coaster, or this whole part of the polynomial, can't represent a roller coaster. And I know that this is when time is 0. So this is where we must start our roller coaster start time. I also know height-wise, I mean, we got to look at this number. This number is 200. I know it's a little blurred. If we look at the remaining stuff going on, it doesn't go higher than 200. We know 200 probably isn't the highest. So since y values represent height, what must be y in between here? So we know y goes as high as 200 feet. But then see how this kind of goes on and down forever? We should probably put a stop to that. So we want to stop a roller coaster. This is 100. 50 seems practical, but all the way down doesn't. So we got to chop our roller coaster off at some point. In fact, I'm going to chop it off right here. So say the lowest it goes in this picture is probably around negative 50 feet. Now I wrote it in math. You can say height between negative 50 feet or 50 feet underground and 200 feet high in this specific picture. So we kind of talked about the negative time and chopping this off. So we know if x represents time, what numbers must x be in between? So x definitely has to be between times in between 0 seconds. And we have to think about time restrictions on a roller coaster. Well, time restrictions on a roller coaster, you don't want to be on a roller coaster for 15 minutes. That's crazy, because you'll get sick for sure. So in this case, if we chopped it off at this mark where it says 50, that's a 50-second ride. So that makes sense. So in this case, we are only going to look from here to represent a roller coaster, which means it kind of tells a story now. Tells a story of, at 0 seconds start time, where do we get on the roller coaster? It tells a story about how deep we go down underneath, how high we rise again, And when we get off the roller coaster, notice we get off at ground level, so we get off the ride on the ground. Makes kind of sense. So let's talk about how to write a roller coaster story. So looking at this, we're going to fill in these blanks. So the roller coaster starts out when I get at the ride at blank feet. So remember, 0 seconds is the start time of the ride. So I must have climbed steps to get on the ride at 200 seconds, or at 200 feet. Then the coaster went where? So I got on the roller coaster and it started. Immediately I went down. For how many seconds? How many seconds did I go down for? So I kept going down until about this spot. So that's about 28 seconds. To a height of how many feet? How far down did I go? I went down to about 50 feet. Negative 50 feet. Then the roller coaster went where? So I'm down. I went up. For how many seconds? How many seconds did I go up for? Well, I'm going up, 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 up. I'm going up until about here, which looks like 48 seconds here. So you went up from 28 seconds to 48 seconds, which is 20 seconds. And you got a little bit above ground. Doesn't look like much, so we'll say about 10 feet. Then the roller coaster went back down. And we looked like we get off the roller coaster at 0, so we went down for 2 seconds to 0 feet. How long did the whole coaster ride take? Well, it went from 0 to 50, so it took 50 seconds. And it drops passengers off at a platform that is, well, look, at 50 seconds, I stopped right on the ground level, so that's 0 feet. How many tunnels were there? Well, I only went underground once, so there was 1 tunnel. And blank amount of drops. Well, how many times did I drop? I dropped once, and I dropped a little 10 feet there, so I dropped twice. We hit the ground at how many seconds? Well, we hit the ground here, right here, here, and here. Ooh, what did those match up with? Those matched up ground with my zeros. 15, 45, and 50. What about this 0? This was at negative 30, though. Why didn't I mention negative 30? Oh, because remember I chopped that off. I'm talking about real life. I'm talking about the roller coaster only in this instance. So see how a polynomial, part of it can represent something in real life, can tell a story. So now